In this video, we present WildPose, a unified monocular pose estimation framework that is robust in dynamic environments. Given a calibrated video sequence captured in dynamic environments, our method effectively detects the moving distractors and accurately estimates the camera trajectory. Most traditional static SLAM methods often fail in dynamic environments. Specifically, static visual SLAM relies on finding dense 2D correspondences and using bundle adjustment to minimize reprojection error. However, the optical flow observed on moving objects is a mixture of two distinct sources: the camera's own motion and the dynamic motion of objects within the scene. Because the static SLAM pipeline tries to minimize reprojection error using all these points indiscriminately, the moving objects pull the optimization away from the correct solution. Current methods attempt to mask out dynamic objects, but often lack robustness. For instance, VIP proposes using semantic segmentation. However, this requires prior knowledge of which object classes are dynamic, limiting generalizability. Furthermore, motion is not always semantic. In this example, one table is being pushed while the other remains static. Conversely, the robot is pre-labeled dynamic based on other sequences, but here, none of the robot moves. Alternatively, WildGS SLAM detects dynamic objects using rendering inconsistencies from 3D Gaussian maps. However, this relies heavily on sufficient camera motion to build a reliable 3D model. In this case, it fails to identify the human body as dynamic because the camera motion was insufficient to observe the static scene behind the body. Here is the pipeline of our method. WildPose robustly estimates the camera trajectory from a monocular RGB sequence. We leverage the frozen master encoder to extract 3D-aware features. Concurrently, a motion mask detector generates motion maps, while we utilize a depth estimator to predict the metric depth prior. These outputs are fed into our update operator, which iteratively optimizes the camera pose and disparity. This process is tightly integrated with a depth and uncertainty-guided dense bundle adjustment module. The motion mask detector takes a pair of images as input. It first extracts multi-layer features from the frozen backbone, then fuses these features to output a motion map for the reference image. We trained the update operator and the motion mask detector on diverse datasets via a multi-stage curriculum. Now let's look at some results. We first present an overview of the tracking performance. We evaluate on 6 datasets: the Bonn dynamic dataset, the dynamic sequences of TUM RGBD, Wild SLAM, 7 scenes, the static part of TUM RGBD, and Sintel. Among all the baselines, our method achieves competitive performance across all these datasets. First, we present results on the person tracking sequence from the Wild SLAM mocap dataset. This is a dynamic and long-duration sequence containing 986 frames. We visualize the predicted motion map in the bottom left corner. On the right, we plot the 2D camera trajectory predicted by different methods alongside the ground truth. The trajectory is error color mapped. Blue indicates low error, while red represents high error. Our method demonstrates low tracking error while effectively removing distractors in the dynamic environment. Next, we evaluate the Cave 4 sequence from the Sintel dataset. In contrast to the previous example, this is an extremely short sequence of only 50 frames. While WildGS SLAM was competitive on the long-duration sequence, it fails here due to insufficient scene observation. Our method, however, remains robust and achieves superior tracking accuracy. Finally, we show results on the static plant sequence from the TUM RGBD dataset. Here, our method also achieves the best performance among all baselines. You may notice that our motion map occasionally assigns high activation to static objects like the plant. This is probably a byproduct of our training strategy. Because we jointly train the motion detector with the camera pose loss, the network learns to suppress not only moving objects, but also potentially difficult features, such as complex textures that could potentially impact dense bundle adjustment. To conclude, we summarize the strengths and limitations of all comparison methods here. Since Droid SLAM lacks a mechanism to deal with dynamic distractors, it performs poorly on the dynamic benchmarks despite being robust in static scenarios. While WildGS SLAM achieves robust performance on most datasets, it struggles with short input sequences, such as the Sintel dataset, due to its need for sufficient data accumulation. In contrast, MegaSAM shows superior performance on the short Sintel dataset, but degrades on datasets with longer sequences. Notably, on the two static benchmarks, both MegaSAM and VIP fail to maintain the high performance they show in dynamic settings. Moreover, VIP requires prior knowledge of which object classes are dynamic. Our method, as shown in the last column, is the only one to satisfy all conditions, handling long, short, static, and dynamic scenes without semantic priors. That's all. The code will be made publicly available. Thanks for watching.